Morning, my name is Destiny, and my chosen article was entitled Exploring the Rhind Papyrus. The article was written by Dana Hartnett and Lauren Kopfle. This article, I believe, was a good choice for me. Not only does it line up perfectly with what we've learned in our math history course, it's also nicely separated by subtopics. All right, so moving on to the first subtopic. We have mathematics as a universal language. So, universal language meaning it is understood by every language in every culture. As a math teacher, I can concur with this. A few times I've had transfer students from across the ocean. They come to America and join a family who offers to care for them while they complete their studies. In the middle of the presentation, I've attached a picture of the Rhind Papyrus, which came straight from my article. So the Rhind Papyrus was discovered around the year 1650 BC. The Rhind Papyrus was groundbreaking for its time. The mathematics that's presented throughout the Rhind Papyrus includes things like circles, triangles, formulas, and even things that helped the ancient Egyptians build the pyramids. So super groundbreaking for the time. We also had ancient Egypt and ancient Greece, which were also in the article here. So both of these civilizations are known for their highly advanced mathematics and astronomy because their scholars reached such a high degree of development in both of those areas. Next up, we're going to look at what is the Rhind Papyrus. The Rhind Papyrus was made of papyrus, or papyri for plural. Papyrus reeds were dried out, perhaps by the sun, and it created a surface which could be written on. Oftentimes, one papyrus sheet was not enough to cover the material, so multiple papyri had to be glued together to create enough surface space for the author to complete their work. Now, this was the case with the Rhind Papyrus. It is 3.5 feet wide and 17 feet long. And from reading the material inside the Rhind Papyrus, scholars have estimated that it's approximately 4,000 years old. So the Rhind Papyrus contained ideas inside of it which were useful for finding volume of barrels for the purpose of measuring the amount of liquid goods to be transported, trading purposes, farming, such as keeping track of the seasons, knowing when to care for your plants and what way, etc., keeping track of the tides, and then also finding volume of a pyramid. This was actually a very helpful tool when the pyramids were built, like I said earlier. And another thing, the thought processes behind the ancient Egyptians was really not that different from ours today. They were more concerned with learning and understanding topics which would prove to be useful in their everyday lives and to simply enjoy the process of learning itself. And this idea does spill into our lives today. As I'm a teacher, I always try to relate what I'm teaching to the students' everyday lives. In Algebra 2, though, it's not always possible, especially because we hit things like imaginary numbers and then exponential functions, and the kids I know are not going to use that. But when I have a solid foundation of real life material to present, I always make sure I take advantage of that. That way the kids are more interested in what I'm teaching them. All right, so another thing that was mentioned inside of the article was circles. Today we see this as an elementary concept. Area equals 2 pi r or pi d. The problem, though, is that 4,000 years ago, pi was not understood. Pi was not even a concept that anybody had even thought of just yet. So the first image here that you see is screenshotted from the article as well, and it shows the Egyptians' method of finding area of a circle using hieratics, and we know hieratics are sort of like a cursive form of hieroglyphics. So as you can see, there's a polygon inscribed inside of a square. The question remains, though, what does this have to do with ancient Egyptians' method of finding area? Well, here's a GIF that I created. We'd start first by drawing a square. The square is a 9 by 9, which we know has an area of 81. We transcribe a circle in such a way that the intersections of the circle and the square are 2 units away from the vertices of the square. Doing this, it shows that there are small bits of our circle popping out of the side of the square. The Egyptians would have cut out the bits of the circle popping out of the square and the corners of the square popping away from the circle. We can do this because of their assumption that both the square and the circle have the same area. So by this logic, it just makes sense that we can get rid of the areas. From this, the formula d minus 1 over 9 times d, all squared, was born. All right, so what would this look like in the classroom? It would look like a whole bunch of foam shapes sitting beside each other to mimic a much larger shape. Students would be instructed to find the area of each of the smaller shapes and add them together. Next, students would be instructed to find the area of the shape as a whole without finding the individual areas and adding them together. This way, students can understand the percentage deficit of using an actual formula as opposed to finding individual areas and adding them up.